Hello, everybody, and welcome back. We are about to have another change in the class. We're going to discuss today residual stresses and distortions in welding, and we're going to do it from a quite fundamental point of view. In that aspect, it's going to be quite similar to mechanical engineering and about stresses and strains. And after we do this, on Thursday, we're going to learn about non-destructive testing. So that's going to be another change because non-destructive testing will bring us some memories of the beginning of the course when we were essentially learning a dictionary, and NDT could just be another class as big as this one, and we'll have it only in one class. And it will be much like a dictionary. What is ultrasound? What is X-ray? What is a dye penetrant? Those type of things. The quiz number 5 that will be on Tuesday will be based on all the material we cover up to Thursday, including MDT. And the following week, in which we still have classes, we'll have 2 lectures on codes and standards, which are to some extent very essential in welding. And what we learn about codes and standards is going to be outside the quiz 5, of course, because we're going to be learning that after the quiz. And after that, it's just everybody has an assignment to do. So you can work on the same things we have done in the exams, but in your own time. And for the grad students, you have a final project in which everybody has a project that was quite carefully assigned for what your interests are and what your research is. And then Christmas. All right. So let's start with residual stresses and distortion. And what I'm going to share with you today is something that everybody sees and everybody knows, but few people could put together in a predictable way, and only us, because of the work in our lab and the work of Mitch Krams that is doing his PhD with us and was the TA last year. He developed some understanding to calculate residual stresses and distortions in things like aluminum, for which there was no systematic way of doing it. So, so you have an idea about like how good that is. When he applied this material I'm going to teach you to pipelines in the International Pipeline Conference organized by ASME in Calgary this year, he got the prize, the best paper award for his work. So it's kind of serious. All right. About reference material, I'll refer you to the Lincoln Procedure Handbook, section 3.1. I'm talking about the 14th edition, of course. Section 3.1 has formulas quite similar to the ones we're gonna see. However, they arrive to those formulas in a very different way, and just by trial and error, and until they got it right based on experience. So let's see. Here I have 2 very colorful graphs, and if you go to meetings or conferences or technical talks about welding, you'll see graphs like this. And the graph on the left is a graph of temperatures. So this red is hot, blue is colder. Question to you. I would like to see in the chat your thoughts about if the weld is, in what direction the weld is moving in the graph on the left, and what direction is moving. By the way, I haven't said it, I kind of took it for granted, but we're showing only half a weld here, not a full weld. Yeah, it's moving up. Thank you very much. Thank you very much. We're on top. So, and we can make these predictions using the formulas you have, using the Rosenthal formula, we can calculate every point in this domain, and using the formulas that you used in quiz 4, you can calculate the maximum width of these isotherms or the length of these isotherms. We can do so much without needing to do finite elements. Now, on the right, we have a graph that has similar colors, but in this case, has nothing to do with temperature and has everything to do with stresses. So this is normal stress in the longitudinal direction. And red in this case doesn't mean hot. Red in this case means intention. You see, it's positive. The convention for stress is that it's positive when it's in tension and it's negative when it's in compression. So, and 0 is around this green. And what do we see here? We see something of much complexity. And I'm going to discuss briefly with you at the qualitative level, so you have a sense of what we're talking about. And we're going to discuss this more later. What do we see? We see that the axis of the weld is this vertical, this edge, right? That is the axis of symmetry. We would see something just the same on the left outside the image. And what do we see? That along the line of welding, we have tensile stresses. And then we see that quite outside of the line of welding, we have compressive stresses. And if we go farther, we have some kind of mild stresses near 0, but there are in tension again, right? This is quite interesting. I want to ask a question that I'd like to hear from the chat. We didn't put the axis here, but typically when we talk about welding in our class, in our lab, the x-axis is in the longitudinal direction of the weld, pointing in the direction of welding. And sigma x is the direction in this, is the stress in this direction. So my question to you is, if I make a cut in the plane, right? It could be this horizontal line at the bottom or at the top or in the middle. I make this cut and I do an integration of the sigma x over this cross section. What number should I get? What should I get? Something big, something small, something positive, something negative, 0. What should I get? If I integrate the normal stress. Okay, here I have a vote for positive. Positive would mean that this is in tension. I have another one for 0, right? 0, I 2-0. So Pavan, I think you're about to be outvoted. Okay, this would be much better to be done in person. And the answer is 0. And why is it? Because if we integrate this stress, the integral of that stress is a force. And if I have a force that is unbalanced, that means my plate will start moving with an acceleration. Force equals mass times acceleration. But of course, in welding, we don't have acceleration. Things are quite where they should be. So right here, we're learning something, that if we have a tensile stress in the middle, right, for whatever reason, which we will discuss, it has to be followed by a compressive stress just to balance it out. And this other part here that looks so complex, as reality is complex, is related to secondary factors. And I'm not going to worry about these secondary factors that gives us these colors. If you're curious, I'll tell you. And this is because the plates are bending in their own plane, right? But among the last slides of today, I'm going to show you that at one point that doesn't matter anymore. Okay, so when people talk about welding distortions and welding stresses, we know this. something's getting bent, something's getting out of place. But if we dig a little bit deeper, we are going to see there are many types of, people tend to call it shrinkage. It's kind of an odd word because it leads some people to believe shrinkage as shrinkage from solidification, or thermal shrinkage, forgetting that before the thermal shrinkage, there was a thermal expansion when things heated up. But whatever it is, and I'm going to use this word shrinkage here just for now, we have many types. Along the axis of the weld, we have a longitudinal shrinkage. Across the axis of the weld, we have a transverse shrinkage. In addition, if I weld the plate, they tend to be distorted. If I weld two flat plates, typically they don't end up flat. And I showed you some images in when we discussed the concept of joining, about how things like electron beam welding could give low distortion in thick sections, but TIG could end up with big distortions, angular distortions in thick sections. And then here we have bending shrinkage. This is the plate seen from the side. And this vertical direction here is the lengthwise direction of the weld. And if the weld is on top, we would have more force on top than in the bottom, and we will end up with a plate being a banana. This distortion in particular, this bending shrinkage, is the key type of residual stresses in additive manufacturing of metals. Way back in the 90s, when I was still doing my PhD, one of my lab mates was doing additive manufacturing of Inconel using electron beam welding. Incredibly pioneering work. And they were using no preheat, and the residual stresses as they were building a wall layer after layer were so big that this banana you see here, it looked pretty much like this. I couldn't believe how distorted things were. Right? Let me tell you more about transverse shrinkage. Transverse shrinkage can be a problem. When we were building the bridge, the new bridge. What's the name of the new bridge? I'm blanking on the name of the new bridge in Edmonton. Any help here? I need to look it up in the map. The new bridge that goes by Kinsman. The Walter Bridge, the Walterdale. Okay, the Walterdale Bridge. The bridge has these two curved beams, and then it has these cross members. And they were afraid that when they would weld the cross members, they would shrink with transverse shrinkage and bend all these other members that were carrying the load. That was a big deal. And they did lots of tests for that. And in the end, it was not a problem. But so you think that bridge that was over budget and behind schedule, those were the type of problems that they were running into. And those were the problems that they could have anticipated had they thought about this ahead of time. The good news, it's not going to happen to you, because you already are going to know that when you get into it. So I'll tell you a little bit more about this, but in this class, of all these types of shrinkages, I want to give you some formula so you get a sense of the power of this shrinkage, how it works, what does it do, and we're going to be talking about the longitudinal shrinkage. We will not talk about transverse shrinkage in this class, other than these words I'm giving to you. We'll not talk about angular shrinkage, right? And bending shrinkage is related to longitudinal. We will talk about that. So about transverse, and this is using words, there is something interesting, that as the plate gets locally hot, it expands, and then when it cools down, it shrinks. So if I have no restraints, right, the plate is going to move out and in as it needs, and we might end up with higher distortions. On the other hand, we can clamp really well. And if you look at the Lincoln Procedure Handbook, has like a whole subsection just on clamping. And you clamp it really well. So when it wants to expand or when it wants to contract, it can't. Good news is not going to be too distorted. Bad news is going to have a whole lot of stresses accumulated, right? So that's about transfer shrinkage. About angular shrinkage, we have a very similar effect. And that's one of the reasons we clamp things really tightly. But it's never perfect. It's never perfect. And multi-pass, and in this class, we'll be talking about single pass welds. Multi-pass welds bring even more complexity. For example, when I make my root pass, now things cannot compress anymore along that line. When after I made my root pass, the hot pass or my filler passes, they cannot shrink anymore because there is something welded there in place. And as they try to shrink, that's what brings angular distortion. Right? And it's quite difficult to understand this effect because each weld brings its own residual stress. But at the same time, each new weld has a tempering effect on the previous weld and can have a little bit of a stress relief effect. All these are words. We're working to turning those into predictive methodologies for engineering. Not quite there yet, and nobody's quite there yet, but we will. About angular distortion, there are some things that are interesting. Let's compare two welds that are with a V groove and a double V groove, right? And as you can imagine, the double V groove is going to end up with less distortions because it's a symmetric joint just to start, right? Whatever distortion the V does now is compensated on both sides. A really good question would be, if both V's are the same, why don't I end up with zero distortion then, right? Well, I'll give you an answer in words. We're working on doing this more rigorously. But this is what happens. Let's say I weld it and I flip it, and this part is welded, and it would have a distortion comparable with what is to be expected from a single V. Now I'm going to do my new weld, but guess what? I'm doing it in already a starting condition that is different than before. And in addition, there might even be some residual stresses in some cases involved. So it's never exactly the same. It's never exactly the same. It's not the same to start with a 60-degree V that if I did the weld on the backside before, chances are that this opening is bigger than 60 degrees. Very interesting. So that is comparing a single V with double V. Double V, because of symmetry, will give you less angular distortion. Now, let's compare with the opening of the V. And guess what? Something that was not too difficult to imagine. As the V is more and more open, the angular distortion is higher and higher and higher. This vertical axis is an axis that is measured how many millimeters for a particular case, as they measure the distortion and see how much one of the sides lifted. I'm not worried about these exact numbers, just the trends. And the trend is that big open V's have a lot more distortion than narrower V's, and I could reduce it even more by having a double V joint preparation. Now, when we discussed keyhole electron beam welding or keyhole laser beam welding, that keyhole that goes very deep essentially is like having a very, very, very narrow joint preparation. It's like having this close much less than 60 degrees. Now, if I do that close to 0 degrees, then I end up with something that is quite close to zero distortion. Some of you might be curious then, so why do we make a V at all? Why don't we make it just a square butt joint? And square butt joints might be okay in single pass welds, but if we have a multi-pass weld, we cannot get there with the torch. Very difficult. So I don't think anybody is doing 120-degree V grooves, right? That's a little bit too extreme. But yeah, 60, 90, those exist. And they are not narrower because you just don't have access to the, to the groove. If you look at old exams, this is a question I asked in those, pretty much as it is here. They are all uploaded. So let's talk about longitudinal stresses. And longitudinal stresses is where we're gonna get quantitative. So we're gonna see how the area near the weld expands and then shrinks, and when it shrinks, ends up with like very high tensile stresses, right? And if we weld this plate along this horizontal axis, this is a typical distribution of residual stresses from a book, and says right near the weld is going to be very high tensile stresses, and then outside the weld we're going to have, guess what, the compressive stresses that balance out the tensile stresses, right? Something I want to bring to your attention. Me, myself, until not too long ago, I used to think that the part that ended up in tension was just the molten, the weld bead. So let me dispel that. The weld bead plays close to no role. If the weld bead is bigger or smaller, you would have distortions even if you don't melt anything, right? We're gonna see what matters for real. Just this week, I got a scientific paper to review of people who knew a lot of math, lots of math. And they were assuming that to calculate the residual stresses, the only part that was in tension was the weld bead. That's not a problem you're gonna have. So in longitudinal stresses, when we have this tensile force around the bead, right? Not just the bead, but the bead and around the bead. If we are making a hollow steel section such as this one, this off-center force is going to, you see, the force that is related to the weld is off-center, and that causes bending. And the Lincoln Procedure Handbook has a formula for that, and you will know where that comes. But in addition, other things can happen. For example, if you're welding thin sheet, and those of you who have welded, probably you have had this experience. If you're welding a thin sheet material and you make a weld that is somewhat thick, you can end up with the weld and the area surrounding the weld wants to shrink, but the rest of the material that was always cold doesn't want to shrink and ends up buckling, looking like this. And it's such a paradox because you start with perfectly flat plate and you wonder what the hell happened. And some people think that when you overheat the plate bends because the heat revealed some internal flaws. No, what happens is that the weld is like pulling a lot of tension, and so these other sides are in compression, and if they are very thin, they are very easy to buckle. Another thing that is seen is that, which actually is a form of buckling, that is twisting. So along this length, this the length along the bead gets shorter because of the shrinkage stresses, and the other parts that were farther from the bead, they never changed temperature, so those never got shorter. And the way they relieve the stress is by twisting. So these sides, while this goes straight and is shorter, these sides now are in diagonal and make it a shorter effective length. Lots of things to learn. And even if nothing bad happened, you know what can happen? If you have a column, the column has a load. Typically in slender columns, the load is given by how much can you take before you buckle. But if you have a welded column, you cannot do a standard buckling calculation, because the column is going to buckle way before you reach the buckle load. And the reason is that the tensile force around the welds are acting as a load. So to the loading capacity of a column, you have to subtract the force that is internal to the column because of the residual stresses. This is very interesting. So to think about residual stresses and the associated distortions, I'm going to use what is a standard way of looking at the problem that is called the 3-bar model. The 3-bar model is a lie. And typically, I tell you lies and I say, well, but it's a pretty good lie. This is a so-so lie. So I'm going to use the 3-bar model to discuss with you what matters. And then I'm going to tell you where it falls short, and we're going to do it right. But in the 3-bar model, what people say is these two, the top and the bottom are kind of very rigid bars, very rigid. And there we have 3 bars, 1, 2, and 3. Bar number 2 represents the weld bead and the area around the weld bead, right? Not just the weld bead, but the weld bead and all the other parts that got hot. Bars 1 and 3 represents the material, for example, in a plate that didn't really see much temperature change. Now you see something of where this would break down, because these bars are very clearly delimited. But in reality, the hot part of the weld kind of is not clearly delimited, right? But for now, if you bear with me, we have these 3 bars, 1, 2, and 3. 1 and 3 represent the plate that never sees much heat, and bar number 2 represents the part that gets hot. So in this one, how does it get hot? It gets hot according to the thermal cycle. And you know what this curve is? This curve is Rosenthal. It's given by Rosenthal's model. So it says everything is cold, and when the heat source comes near, temperature increases, and then after reaching a maximum, it cools down. So we have 2 parts of the cycle. We have a heating part of the cycle, and we have a cooling part of the cycle. We start at the preheat temperature, we reach a maximum, and then it goes down to something that typically is back to the preheat temperature, right? It's here, it says T infinity, but it's a subtlety. It goes back to pretty much the preheat temperature. All right, so that's how the metal. Now let's talk about the middle bar. Let's say that the bars at the edges are big and stiff, but let's say the middle bar has these material properties, 2 of which you're very familiar with. Those of you who did your undergrad at U of A, you have seen this in MatE 202. And pretty much everybody else, from chemies to mechies to civies, have seen this curve. This curve is the behavior of steel under tension. So in the horizontal axis, we have elongation, right? And elongation in percent of elongation. So if the bar was 1 meter long, 1% elongation means is 1 meter plus 1 centimeter. And in the vertical axis, we have the stress, right? That is the load divided by the cross-sectional area. And I'm not gonna worry right now about engineering stress versus true stress. It's let's go easy about this because we don't need to worry about necking in this case. How does steel, or how do most metals typically behave? Most metals, how they typically behave? When we have no load, we have no stretching, we have no elongation. But as we increase the load, we start to increase the elongation. Now, that comes to a limit. There is a point at which, if I keep stretching it, the bar doesn't take it, or oh, something I forgot to say. As we stretch this, what is happening is the atoms get a little bit more separate from each other, but no atom is really moving, right? So when I unload it, the atoms recover their original distance, but because no atom moved, everything went back to the beginning. That is what is called the elastic behavior. Now, it gets to a point in which I try to stretch it too much, stretch, and at one point, the atoms start slipping past each other. It's not anymore that they are just stretching their bonds a little bit, but now they are changing their bonding, right? And those of you with some background in materials will remember that what is happening is dislocations start moving, and as the dislocations move, they cause this plastic effect. When I relax the load, those atoms that move don't go back to its original place because they move by changing the bond with each other. That happens at a load. So we start stretching elastically. It gets to a point in which we reach what is called the yielding, what is the yield stress or the yield strain. And we start having this effect of the dislocations moving, the atoms moving past each other in a way that they will not recover. Most materials, as they move, they generate new dislocations. So in reality, they start to get harder and stronger. That is what is called work hardening, right? And the curve from this point starts to move a little bit higher. Interestingly enough, the structural steel often has an almost perfectly elastic plastic behavior in which once you reach the yield stress, you stay at the yield stress more or less dead on for quite a bit as it stretches. In our analysis, we're going to be considering this simpler case in which there is no strain hardening, and we go from elastic to plastic. Stay there, right? What do these formulas say? Because you see the Greek letter, they might be somewhat intimidating to some of you, but says the total strain is given by an elastic component of strain and a plastic component of strain. From the atomistic point of view, it means this. If I stretch my material, some amount of stretching is because I moved the atoms past each other. That's a plastic strain. But as the atoms made new bonds, in addition, those bonds are a little bit stretched, even before I move them on, right, to the next atom. That's the elastic stress, the elastic strain. So I move the atoms past each other, plastic strain. I stretch the bonds, elastic strain. So let's go back to our model of residual stresses. let's say we have our 3 bars and we're all at the preheat temperature. Let's say it's room temperature. T naught, T naught, T naught. What's the load? 0 is the load. 0 is the load. Nobody's loading this, and everybody's happy. We would be at this point in the temperature history. Now I'm going to start moving a little bit to the right, and I'm going to see how at different times temperature starts to go up and then comes down. So let's see what happens as I start moving a little bit to the right. When I increase okay, let's do this. When I increase the temperature, right, the middle bar is going to want to stretch because of thermal expansion. And the columns on the sides, no, because they don't see the temperature. They are where they were. But this column in the center wants to stretch. But guess what? It cannot really stretch because we have this crossbar here that makes all bars to be of the same length. So as we try to stretch and we reach this high temperature, the bar would be putting, this crossbar would be putting this middle bar in compression. And the compression can be quite strong. And actually, in welding, I don't know any case in which you don't reach yielding in that compression. So keep this in mind. We were talking about how the residual stresses in welding are in tension near the weld. But what I'm just saying is at this one stage in our problem, as we heated it up before cooling, what we have is compression, right? It's compressed, and it's so compressed that can be yielding. Let's see step by step. This is the material behavior that we have, right? In this case, we put the absolute value of stress. This is in compression. So we start to move, and this graph is, this is appropriate. Here we have the, as we increase the temperature, we increase the strain, right? And we would have, okay, we start increasing the load, increasing the strain, that now will be an elastic strain. A little bit more as I increase the temperature, a little bit more. As I increase the temperature, now I would have reached in compression, as the bar wants to expand and it cannot expand, reaches yielding. And as the bar still wants to expand and it can't expand, reaches, has even more plastic deformation in compression, has a plastic deformation in compression, right? And then guess what? Then we want to cool, right? Like after the weld, after the torch passed over the point, it wants to cool down. And it cool down, let's say it goes back to T naught. Let's say that the bar breaks here, so it shrinks. We would have no stress there. But in reality, everything is attached. So what do we have? We need to have a tensile stress to bring it back to its original site. This is the origin of the final residual stresses as being tensile near the weld. It's because it plastically got smushed during the heating cycle, and then in the cooling cycle, it wants to cool down, but it just happens that it's too short. And that's why it ends up in tension. So what does it look like? We were in plasticity and we start to unload, right? And in this other graph, we go from plasticity and we unload. And as we unload elastically. We unload elastically, and now it depends on how much it deformed, right? How much plastic strain we have. As we unload, maybe after we unloaded elastically, we go from, oh, this was in compression, now it's is less compression, even less compression, now it's in tension. And it can be to a point. And by the way, in welding, I don't know any case in which you don't reach this point, in which now when it wanted to shrink, starts to shrink in plasticity again, right? It starts shrinking in plasticity again. And you end up at the, you end up at the original temperature, more or less, but with residual stresses in tension. So, what do the red, yellow, and blue lines mean? Okay, let's see here. Here we have total strain in the bottom, and here in the vertical we have elastic strain. So, as in the red line means we are loading elastically. Red line means loading elastically. Then the orange line here means we are keep loading it because the temperature keeps increasing, but it's plastically. And this increase that in strain we see is all the plastic strain. So this is initial condition. This is increasing temperature. This is still increasing temperature. And then this point is the point at which we reach maximum temperature. And then we start to cool down after the maximum temperature. And after the maximum temperature, we start to unload. But the first unload is elastic. So we are unloading all the elastic forces. It gets to a point at some temperature in which we go through no force at all, no elastic strain. Oh, sorry. And then it might still keep shrinking and keep shrinking elastically, but now it's in tension and it keeps shrinking and depends on the case. But when you're near the weld, this shrinkage reaches the elastic limit and starts to shrink plastically. And this is the purple part of the curve. Shrinks plastically. And the final stress at this point is going to be yield stress. So, Jolene, did that help more or less answer, or should I go over this again, or for anybody else? Okay. Okay. So there are two interesting temperatures here. When we are heating things up, we heat it up until we reach a temperature, let's call it characteristic temperature 1. That is, we reach the temperature at which we reach yield during heating, right? Any temperature above this means that we are well into yield of our middle bar, yielding in compression. And then when we cool down, right, we are going to reach at some point another, we're going to reach yielding, and we can reach a lot of yielding as we cool down, and the yield would be in tension. But the very beginning of reaching yield in tension, that very beginning, that would correspond when we start from a maximum temperature, we're going to call it delta T2, right? So we have these two critical temperatures. One critical temperature at which the middle bar wants to expand, but cannot expand anymore and reaches plasticity. And then another temperature at which this bar is heated so much that when it wants to cool off, reaches plasticity again, but in tension. So this 3-bar model is a very important analogy. All right. So something interesting is you would imagine that the temperature to reach yielding is high, but in reality, it takes very little temperature to reach yielding in most materials. For the case of steel, A36 structural steel, which is what is commonly used, this temperature is of the order of 100 degrees C. So when you're welding something, any point that would make the water boil typically is a point that is yielding. By the way, that's quite far away from the weld. It's not the weld bead, it's actually quite farther away. And when you reach something of the order of 180 degrees C, right, you're not only reaching plasticity, but when it cools down, it's plastic again. This is pretty radical, right? To realize that we're going to end up with these residual stresses that are even at lower temperatures, way below the bead. The bead has a maximum temperature of, say, the edge of the bead is 1500 degrees. The edge of the bead is 1500 degrees. And we say that yield happens at 100 degrees C, way outside the bead. So the ratio between these temperatures, this yield temperature in cooling and the yield temperature in heating is a factor of 2, and we're going to see that it appears. So we can calculate the amount of plastic strain, how much it was deformed plastically, as how much it was deformed by expansion in total, and we subtract the limit at which was elastic. And because it all depended on temperatures, this would be the maximum temperature minus this yield temperature. And this alpha is the coefficient of thermal expansion. Oh. Yes, let me move forward with this, and if we have time towards the end of the class today, I can go over this explanation again. So actually, I think we'll all benefit from this. When I asked if it was understood, nobody said yes. So let's go back to the residual stress. Three-bar model. And in the middle, the two bars, number 1 and bar number 3, are always at preheat temperature. Let's call it room temperature. Bar number 2 in the middle goes hot and then cools down. The material we're going to consider is like an elastic, perfectly plastic, right? So as we stretch it to a point, the atoms stretch a line, but then when we let go, it goes back together. And if we stretch it too much, it starts yielding. So in this model, we would say, before we apply the load, before the middle bar sees temperature, everything is the same. When the bar starts seeing some temperature, it's going to want to stretch. If it stretches a little bit, and this stretch is not possible in this case because of the crossbar. In the case of a weld, it's not possible because it's the same plate and all the rest of the plate is cold. So the center cannot stretch. I cannot start squeezing out middle material, right? It's all tied together, right? So the middle material near the bead wants to stretch, but it cannot stretch. Would be like if it wants to be bigger at no load, but in reality, it's the same size, get compressed, and reaches, depends on how much it wanted to expand, it can reach yield stress. doesn't get any much more than yield stress. But what happens is, as it wants to expand more and more, with the same yield stress, starts having more and more plastic deformation. So here are the curves I was asked about. At the beginning, the middle bar wants to stretch thermally, and if it stretches only a little bit, it stretches elastically. It gets to a point in which it reaches the elastic limit, and if it stretches any more, the horizontal axis here is the total strain. If it stretches any more, then we start having plastic strain, motion of dislocation. So red is the bar wants to expand elastically, but cannot, so it starts accumulating loads or elastic strain in compression. When it reaches the limit, starts to accumulate plastic strain, and it can keep stretching, right? And then it and then after it reaches the peak temperature, it cools down and wants to shrink. If it could, it would get shorter, but it cannot. It cannot, because it's all attached to the part near the weld. It's attached to the rest of the plate. So to make it be the same size, we would need to stretch it. And depends on how much we stretch it, it can reach yield again. So as it cools down, it starts first giving up the elastic strain, right? It gives up the elastic strain and stresses. And this was in compression, but it's every time less and less in compression, and still wants to shrink, and still wants to shrink, and gets to the point in which it wants to shrink so much, but it can't, that reaches yielding. And this is the purple part of the curve. And what I wanted to bring up is there are two important temperatures. One is during heating, the temperature at which it starts yielding in heating, that we call delta T C1. And this is more or less 100 degrees. So when you are welding, when you see 100 degrees, the material starting to yield. And then there is another one that says, if you put enough plastic strain during heating, when it cools down, eventually will reach yielding too. And in that case, that is the temperature at which we would start having yielding during cooling, we will call it delta TC2. And that is of the order of 180 degrees C. And the final stress in this part will be a tensile stress of the order of yield stress. So in in this 3-bar model, what we see is that the amount of plastic strain, right, is related to the total thermal strain, which is related to the thermal expansion coefficient, minus the elastic component, right? And the elastic component was given by this yield temperature, delta TC1. So what do we see? We have seen when we started to discuss our module on temperatures that how the maximum temperature at each point, right, it was the farther away we were from the weld, the lower the maximum temperature was. And this is kind of a schematic of each point, what is the maximum temperature it would see. Now, this maximum temperature, right, gives us, when we multiply the maximum temperature by the thermal expansion coefficient, gives us the total strain. And we said that any strain above this, the strain given by the yield temperature would be, any temperature above the yield temperature would result in plasticity. And when we reach the delta TC2, that is plasticity during cooling, we know we're going to end up with a final residual stress that is yield stress. So in our final state of stress is going to look like this one here. This mount is the residual stresses in tension due to the plasticity. This is where it had plasticity both ways. This is yield stress. This part is when it sees plasticity during heating, but not during cooling. And this other part here, right? These kind of wings, they're the wings that are in compression to make up for the tension in near the weld. I want to be clear, this width here is not the width of the weld bead. This width here, this is the width of the isotherm of 200 degrees. The width of the weld bead is the isotherm of 1500 degrees. This one is the isotherm of 200 degrees. This is much, much bigger, much bigger. This compressed part in a big plate is negligible. So we can forget about this part now, because it's just the part in compression. This load here, and I'm going to, this area here, that here we have tension, here we have compression. If we look only at this area here and we integrate it, right, that is what is called the tendon force. If we integrate this area, it gives us how much force the weld is pulling, right? So because of heating and then cooling, we have residual stresses, and the residual stresses are much broader than the weld bead. The residual stresses reach down to 100 degrees C in structural steel, while the bead reaches only up to something that is more or less 1500 C. So this is much broader. If I integrate all these residual stresses in this broad region, that integration of residual stresses over the cross-section, over this cross-section here that had plasticity, that is what is called the tendon force. It's because it's a tendon like those in the Achilles tendon, right? And that tendon force is what is pulling the weld and what is causing distortions, buckling, twisting. So I'm not going to ask you in the exam for you to do the derivation, but I want you to know these basic things, that welding during heating gets into plasticity, during cooling gets into plasticity again. And this area in plasticity is much bigger than the weld bead. And it's your great fortune that we have at the lab done, Mitch, our PhD student, done so much work in trying to predict this. And we have formulas for that. And this is a formula for the tendon force. And it's very similar to the formulas that you saw in the temperature-related properties, right? Like thickness of the heat-affected zone. It says, the tendon force is square root of 2 pi e, that's a number, log of delta TC2 over delta TC1. You might or might not remember, but this ratio, for what we will be using in the class, the ratio is 2. There are cases in which it's different than 2, not too far from 2, but more or less 2, but not exactly 2. I'm not going to worry about those right now. So up to this point, we have just a number, if we say this is 2. Now here we have E is the Young's modulus, alpha in this case is the linear coefficient of thermal expansion, which is tabulated. Rho is the density of the material. C is the thermal capacity of the material, the specific heat of the material. And this is Q in watts, effective because all that matters is what comes in, divided the travel speed. This term here is the actual heat input in joules per meters, right? Or kilojoules per centimeter. This is super important. If you think of this formula, you might notice something. Before I tell you about this formula, what do you think? A strong material, I have a strong material and a weak material. Do you think the strong material is going to have higher tendon force? Interesting. Well, if we look at the formula, yes, I would have thought the same too. But let's start by looking at the formula. Nothing in the formula relates to the yield stress. So regardless of the yield stress, I'm going to predict the same tendon force. And here's the amazing thing. And not everybody knows this. Because we know that this tendon force comes from plasticity, and we know the amount of residual stresses, the magnitude of the residual stresses is the yield stress. Yes, it is true that the stresses will be higher in a stronger material because it has higher yield stress. But the area on which we have yielding is a smaller area because it's a stronger material. And when you do the math, the crazy thing is that they cancel each other out. So stronger materials give you higher residual stresses, but in a narrower range. And if you combine them together in an integral that has a higher peak but a narrower domain, the number is the same. Isn't this crazy? That's amazing. So things like stainless steels have higher distortions because the coefficient of thermal expansion is higher, right? But it's not because they have lower strength. So interesting. So this formula, which we already knew, we can combine with these concepts we have, but I'm not going to ask you about the derivation, but I want you to be able to use this formula here. If we say, imagine we have a plate. Imagine we have a plate, not a girder. Imagine you have a plate. Now let's talk about the compressive stresses. The compressive stresses are going to be the tendon force divided the thickness and width of the plate, or the final membrane, right? The two plates together. There is something even more interesting. You see E alpha over rho C. If you do it together, this is based on the laws of physics, pretty much a constant number that, give or take some coefficient, is called the Grunweisen parameter. And it's more or less constant for all materials. Look at this, 836. If I do, this was a number, this was just a number. This one I'm telling you is pretty much a constant. And this is effective heat, this is heat input, right? We wrote it as power over velocity, but this is heat input. Look at this. This coefficient would be 0.22 for structural steel, 0.25 for stainless, 0.2 for 4340, right? It's pretty much very much the same along materials that if you go from Inconel to aluminum, very different, right? And their coefficients are more or less the same. So let's do an example, and then in the I don't know if I'll have time for you to do it during the class, but during the seminar we'll do another example. I would like to do a few examples in preparation for the quiz. So this is a sub-arc welding procedure, right? And the question is, if we are doing 10 gauge sheets, these ones here, and with this procedure. What is the tendon force going to be? Well, look, after all I talked, I hope you got a kind of some sort of an intuitive sense, hopefully. But in the worst of all cases, here you have the formula. The tendon force is C1 times the heat input. And here we have the thermal efficiency of subarc welding, 0.99, the voltage that they tell us, 28, the current that they give us, 675, and we get how many watts. This is the QF here. The U is the travel speed, and in this case we have it in, they call it arc speed, but it's a travel speed, 120 inches per minute. So we'll need to do the conversion, and we multiply by C1. It's 836 steel sheet. So we go to 836, it says 0.22. And here we have the 0.22. We do the calculation, and what we end up with is 81 kilonewtons. 81 kilonewtons is quite a bit. It's like 8 tons. More or less 8 tons. That's a lot. That's just because of the weld. So now all these tensile stresses in the weld, and it's not just the weld bead, right? It's wider than that. This will induce a compressive stress in the rest of the plate. So now let's say that the plate is actually not very, the plate is not very wide, right? Is 10 inches wide, right? On each side. Each of the plates is 10 inches wide, 250 millimeters. So what would be the compressive stress in this case? So we use the same calculation we discussed before, and we use the concept of weld as a line. We say this tendon force is just a force in a line, right? Divided the cross-section of the plate. So the thickness was 3.4 millimeters. If we do the conversion, the width is 250 millimeters for total. And that gives us like 50 megapascals. So 50 megapascals is kind of an okay load, but it's not negligible. Now, if the plates, instead of being 10 inches wide, were like 10 feet wide, as many things in civil engineering, so then this compressive load would be really, really negligible. That's why for this class, we're assuming that the effects of a compressive load in modifying our calculations are very small. And we calculate the compressive load as if it wouldn't, as if it is decoupled from the tendon force. More, bending distortion. So again, for the mechis here, we'll say, or civis here will say, oh, this is trivial. For some others will say, oh my God, what are all these formulas? These formulas are included here. So if you ever need them, you have them, but they're typically in engineering handbooks. But this is the point. If you do the weld, right, making a hollow steel section, as I showed you as an example at the very beginning of the class today, and you weld it at the edge, right, that weld is off center. And now you know that this weld is going to have this tendon force pulling. And these formulas tell you how much a beam is going to bend for a given load you put in it. In our case, the loading is the loading of a moment, and the moment is the tendon force times to the distance to the neutral axis. So you don't need to do the derivation, but this is the formula that would give you for a beam like this, what is the deformation when it bends? If you put it on the floor and you measure how much light is there, that light is going to be given by this formula here that has the tendon force, length of the beam, the distance to the neutral axis, the Young's modulus, and I is the moment of inertia, which is tabulated. So let's do an example. Let's calculate the deflection of 1 meter long hollow steel section of 8 inches by 2 inches by 1/8 in thickness, right? That is fabricated in a single pass with a single MIG pass on the top. And by the way, when we did this problem, we used the values from the procedure handbook to suggest something reasonable. And here we have the values. So we would calculate we need to know in this case, to use this formula, we need to calculate the tendon load. So the tendon force, the tendon force, if it was structural steel, again, is like 836, is C1 is 0.22 times the heat, the heat input, right? And for that, the heat, the power is thermal efficiency times voltage times current, which were given, and the travel speed is given. And in this case, we get that the tendon force is 65 kilonewton, which again is a lot. That's more or less 6 tons. Now, to apply the formula, we needed to have the moment of inertia, which is typically tabulated. That's one of the beautiful things of civil and mechanical engineering. They have these things already done. So the hollow steel section of 8 by 2 by 1/8 will have a moment of inertia of here 15.7. Here we have it. And so we have to convert this 6.53, and it appears here. Young's modulus, moment of inertia, the tendon force we calculated, length of the beam, and distance to the neutral axis. And what it says is that this beam is going to bend about a little bit more than 0.5 millimeter, 0.6 millimeters. This calculation we have just made is extremely powerful. We can calculate bending of things during welding. Let me put all this together, because now things get to really an incredible point. We said that this deformation in the bending of a beam can be calculated with this formula that mixes strength of materials with the tendon force. And the tendon force came from our understanding of temperatures and the yield stress of the material, right? So this formula we just discussed was the topic of today. And we could calculate the tendon force. And we also said something that is especially interesting. If you remember when we talk about mass conservation, if we started with the cathode fault voltage and the anode fault voltage, right, we could calculate, if we combine that with the position rate, we could calculate a relationship between how much material was deposited and the heat input. So here we needed the heat input, and here we have a relationship between the cross section of a weld and the heat input. And this is the exact number we used by that came from using our values of voltage for the electrodes, and was 60 joules per cubic millimeter, right? That's what you're gonna find in the mass conservation unit. So if we say for MIG is more or less 0.7 thermal efficiency, we combine all this together, right? This nominal times efficiency would give us the effective value times 0.22 gives us the tendon force. And if we combine all this, we get this formula, which we have done from first principles. We didn't invent anything, first principles, and says that the deflection is this coefficient of 5.5 times 10 to the minus 3 times the cross section of the weld, length of the beam, distance to the neutral axis, moment of inertia. And here you have formulas from the Lincoln Procedure Handbook. And look at that. The formula of the Lincoln Procedure Handbook is pretty much exactly what we have done from first principles. But you know how they did it? They knew strength of materials, and they assumed that there was a force that was stronger or proportional to the cross-sectional area of the weld. They didn't know why, and nobody knows how they derived these formulas. What I suspect, in the book it doesn't say, none of the book says, and I asked Professor Dwayne Miller, that is Dr. Blodgett's successor, said, do you know where this comes from? He says, I don't, and there is no records of it. What I suspect is they measure a lot of bars bending, and they came to with this coefficient empirically. But now you know where it comes from. And they never did it for aluminum. But we don't need to, because we can do it. And if you want to calculate bending in titanium, now we can. This is the amazing thing of having broad understanding. The amazing thing of the patience you have had to learn a dictionary, learn metallurgy, learn plasma physics, learn heat transfer, learn stresses and strains. But when you put it all together, all of a sudden, now we can make very practical predictions, knowing where it comes from. And in addition, we can make predictions for things that nobody else could make, because there is no such thing for aluminum. One last thing that I wanted to show to you. In these calculations, I want to show you the effect of the plate length. When we use the concept of weld as a line, we assume that the line is narrow and long. But imagine the plates. It is a square plate in which the weld wouldn't be so long, right? Like the plates, there's lots of the plate is too short to consider that the line is long. And what we see is this tendon force in these edges, right? It causes some amount of strain, right? And this is what we call edge effects. And this strain, in the case of a square welding two plates that form a square, these edge effects actually reach the whole weld. But when the weld, the ratio between the plates combine, right, when it's 2 times as long as it is wide, the effect is less than 5%. So these formulas we have discussed, they're good when you're welding something that is twice as long as it is wide. If it is shorter, these formulas start to have errors. This curve we have here is the excess in strain due to this stress concentration and in the middle of the plate. So when the plate starts to become longer and longer, this excess in the center goes to zero, becomes negligible. Okay, this is the last slide I wanted to share with you with this. Let's take 10 minutes. I will ask you, all of you, to check your email, because I sent the final exam of last year, and I want to go over 2 problems of the final of last year to do it together to make sure you are able to do it. I'm going to divide us in break rooms. Okay, I'll see you at 3:30.